Alright, today we're going to be talking about functions and their properties. So defining a function in graph form. If the graph passes the vertical line test, it's a function. The vertical line test means that every vertical line drawn can only touch one point on the graph. If it ever touches 2 points at the same time, it's not a function. So use the vertical line test to determine whether each graph is the graph of a function or not. Well, you see how every vertical line I'm drawing only touches the graph one time. One intersection point, 1 point, 1 point, 1 point, 1 point. None of those lines touch the graph twice at the same time. So yes, this is a function. Same with this one. There's no way I can touch 2 points on that graph at the same time with one vertical line. So yes, that's a function. So far it's a function, so far it's a function. Right now it's not. Because actually I hit 3 points. With the same line, I hit 3 different points on the graph, so no, this is not a function. Okay, so you try this one, hit pause, come back when you're ready. And obviously, no. This one. Oh, why is it yes? You're going, look, I can hit 2 points with the same line. Yes, you can. But this one is open, which means it doesn't count. So this one line is only really hitting 1 point that's defined by this graph. So yes, this would still be a function. Alright, so how do you determine whether or not a relation is a function? If it passes the vertical line test. Alright, an equation is a function if it takes an input and gives exactly one output. Okay, so if you can't draw, or you don't have a graph, you just have an equation. What it means to be a function is if for every input you get exactly one output. So if I look at some examples, this is going to be a line, but watch. If I plug in 5, I get y equals 2 times 5 plus 4. Which is 10 plus 4, which is 14. So my output would be 14. If I plug in 0, I get y equals 2 times 0 plus 4, which would be 4. So I get an output of 4. If I plug in negative 6, I get y equals 2 times negative 6 plus 4. That's negative 12 plus 4 is negative 8. If I plug in 101, I just picked some weird number. I get y equals 2 times 101 plus 4. That's 202 plus 4 would be 206. And what you're seeing is these are all different. I don't get the same y when I plug in different values. So yes, this is a function. I also know it's a function, guys, because it's a line. Okay? If you have a first degree equation, you have a line. A line is always going to pass a vertical line test. Let's look at this example, though. We have 4x plus or minus 3. Well, if I plug in 2, I get y equals 4 times 2 plus or minus 3. So I would get 8 plus 3, which would be 11, and I would get 8 minus 3, which would be 5. I get 2 outputs for 1 input. So no, this is not a function. Okay? Alright. Well, if we look at this one, I got y minus x squared equals 0. If I plug in 5, I get y minus 5 squared equals 0. So I get y equals 25. Negative 5, y minus a negative 5 squared equals 0. That's going to be y equals, well, this would be y minus, that's going to be positive 25 equals 0. So again, y equals 25. Excuse me. And when I plug in 6, I get y minus 6 squared equals 0. So y equals 36. Excuse me. Sorry. And if I plug in -3, I get y minus -3 squared equals 0. So that's going to give me y minus 9 equals 0, which gives me 9. So I got one output for every input. So yes, that would be a function. Alright, plus I know this is a function because this is going to be a parabola that opens down, and that will pass a vertical line test. Now when I have this one, if I plug in 25, I get 25 minus y squared equals 0. I'm going to add y squared to get rid of the negative, so I got 25 equals y squared. Square root of 25 is plus or minus 5. Again, I get two outputs for one input, so no, that's not a function. Okay? Alright, defining a function in equation form. Do the exponents tell us anything? If you're given an equation and asked if the equation is a function, or asked if the equation defines y as a function of x. And I just want to show you some things to see if you notice anything about the exponents. If I graph this, it's a line. It passes the vertical line test. If I do it backwards, it's still the same graph, and it passes the vertical line test. Notice that my degrees are ones. Okay, what about squares? Well, if I type in y equals x squared, this is my picture. It passes the vertical line test, so that's yes. If I type this one in, which to type it, you have to get y alone, so you would have to type y equals plus or minus the square root of x. So the way you type that is you have to type two separate ones, and I type positive square root of x and negative square root of x. The reason, and I just typed it in radical form. Remember, that's a 2, that's a 1, so that's x to the 1/2. So I typed positive x to the 1/2 and negative x to the 1/2, and you get that, which does not pass a vertical line test, so that's no. Notice what happens when you're squared. If x is squared, it's still a function. When y is squared, it turns it sideways, which won't pass. Okay, let's look at cubes. If I type in y equals x cubed and I graph it, I get this s-looking thing, which passes, so this is a function. Again, if I do this, I got to take the cube root of both sides to get x alone, so I have y equals the cube root of x. And I don't need plus or minus, not when that index is odd. You only need plus or minus when it's even. So I type that x to the 1/3, and I graph that, and yes, that passes the vertical line test. When it's cubed, they both passed. When it was 1, they both passed. When it was 2, it passed if x was squared, but not if y was squared. Alright, let's look at x to the 4th degree function. Kind of looks like a parabola again. It's really not, but it passes the vertical line test, so yes. To do this, you'd have to take the 4th root on both sides, and again, that's going to be plus or minus because that index is even. So I have to type positive x to the 1/4 and negative x to the 1/4, and I get this picture, which does not. So what do you notice? Well, to me, if the exponents are odds, they're functions. If they're even, then as long as it's on x, it's a function, but if it's on y, it's not. Food for thought. Alright, so checking domain and range values. It says, remember, an equation is a function if it takes an input and gives exactly one output. So, if I graph y equals x to the 7th, I type that in. I get this picture. Again, an odd function kind of gives me this s-looking thing. And yes, it's a function. Alright, if I do this one, I'd have to take the 7th root of both sides. So y would equal the 7th root of x. I don't need plus or minus because 7 is odd. Oh. I don't know why I did the table. Oh, so you can see that every input gives you exactly one output. These are all different. Okay, so if I type this one in, x to the 1/7, I get this, which yes, passes. And you can see on the table, all the y values are different. Okay, so, where are all the x values? So if I do x to the 10th, and graph it, I get, again, kind of a parabola looking thing. And if you look, you get one output for every input. If I do this one, I'd have to take the 10th root of both sides, which is going to make me have to do plus or minus. And I get the sideways one, which won't pass. And then you see you have all these error messages, okay, because it's not defined. It doesn't go, there's no graph over here. That's why those are all error messages. All right, and that means it's not a function. All right, so it says determine if each equation defines y as a function of x. It's a line. First degrees are lines, so I know it does. But if you're not sure, graph it and do the vertical line test. This one is a y squared, which means it's going to be a sideways parabola, which means it's not going to pass. To type it in, you'd have to type a positive, because to get y alone, you'd take the square root of both sides, which I'd have to do plus or minus. And sure enough, it's a sideways one, which no, does not pass. When you have x squared plus y squared equals 16, I promise if both of these are squared, you're going to end up with a circle or some sort of an ellipse or something like that. But either way, it's not going to pass the vertical line test. And to type this in, to get y alone, I'd have y squared equals negative x squared plus 16 square root. I'd get y equals plus or minus the square root of negative x squared plus 16. So to type that, you'd have to type that positive and then that negative. And you get this circle. Now it doesn't draw it very well, but it's connected. And that does not pass a vertical line test. Okay, a squared function. When you have a squared function, you have a parabola. Parabolas pass. As long as it's x squared and not y squared. So yes, that one is. This one, when you have x in the denominator, you're going to get these undefined. You're going to get these gaps in your graph. Okay, but this thing still passes the vertical line test. So yes, it's a function. All right, so you determine whether this one is or isn't. Hit pause. Come back when you're ready. And yes, if you graph that, it's a horizontal line, which passes the vertical line test. Okay, try this one. Hit pause. Come back when you're ready. And this one is no. And the reason is, once I get y alone and square root this, that's going to be plus or minus, right? And you get this hyperbola looking thing, which does not pass a vertical line test. Alright, so how do you determine whether or not a relation is a function? Well, you can look at the graph and do vertical line test. You can look at tables and make sure that all of the x's are different, or that every input gives exactly one output. Alright, finding the domain of a function. Your domain is kind of like this. When you have an equation with an x in it, okay, you're basically inviting all of these x's to come over to this function party, okay, that you have. But only certain x's are allowed. You are not going to allow any x in your party that is going to cause a denominator to be 0. And you are not going to allow any x's into your party that's going to make your radicand negative, if you have a radicand. Okay? And so what you do is you take your denominator and you say, Mr. Denominator, you may never equal 0. And to figure out what restrictions, what x's can't come to your party because of radicand issues, you say, Mr. Radicand, which is what's under the radical, you must stay greater than or equal to 0. Okay? So, finding the domain of this function. Are there any denominators? No denominators. Are there any radicals? No radicals. Then there's no drama. No drama means your domain is all real numbers. That can also be written as round bracket. Your domain goes from negative infinity to infinity. And what that means is every x in the universe is welcome at this party. There's no drama going to happen by an x coming that would make a denominator 0 or make a radicand negative. Okay? Every x is welcome. There's no bad x's for this problem. And if I look, again, if it's a function, your domain, all right? Well, not necessarily, I guess. I shouldn't say that. Okay? But your domain, this goes forever, never left, and forever, never right. Your domain is all real numbers. All right, so this problem, we have issues. We have drama. We have denominator drama. The denominator drama. And my denominator drama says, Mr. Denominator, you may never equal 0. So I got to figure out what x could potentially make that 0. And I don't want to let him in the party, because if I let him in the party, we're all going to jail. All right, because it's illegal for that to happen. So to get x alone, add 4, x can never be 4. If it is, this denominator, if I make x 4, 4 minus 4 is 0, you can't divide by 0, that's illegal. So every x in this universe is welcome except for 4. What that looks like is, he can't come. All of these x's are more than welcome. All of these x's are more than welcome, but 4 cannot come to the party. You are not welcome at my party. If you come to my party, you make my denominator 0, and I go to jail. So, no. So what we say is, if you write this in interval notation, your domain starts at negative infinity, goes to 4, can't have 4, so use a round bracket. Union, it's going to start again at 4, not including 4, but it's going to start again at 4 and go to infinity. So that's how we tag it up. My domain would be negative infinity to 4, union 4 to infinity. Okay? And if you look at this at 4, 1, 2, 3, 4, you'll notice the graph jumps. Again, it won't draw that line in there for you, but you know that's why there's a gap there, because at 4, we go to jail, so we do not go there. We just skip over it. We'll graph on this side of it, we'll graph on this side of it, but we ain't touching it. Okay? Alright, so on this one, I've got 2 sets of drama. I've got denominator drama, and I got radical drama. Okay? So you just do them separately. My denominator drama says, Mr. Denominator, you may never equal 0, so x may never equal 4. So I put a hole there, and I color everything else. There's my denominator drama. Okay? Now, if I do my radical drama, and this is only when you have an even index. If that's an odd, it's not even drama. Okay? Radical drama says, Mr. Radicand, or you could write the whole thing actually, that radical must stay positive, because if it's negative underneath there, then it's, again, imaginary, and that's not allowed. So we do not want any x's coming to our party that would make that negative. So if I solve it, square both sides, I get x plus 3 has to be greater than or equal to 0. Minus 3 minus 3, this says x has to be greater than or equal to negative 3. So if I put that drama on there, negative 3 is down here. It can be included, and it says everything to the right. So who can come to my party then? What x's are and what x's are not allowed? Well, it's the union of these. Okay, if there's red and purple, those x's can come to the party. If there's only red or only purple, they can't. So this section has only purple. No. This section has red and purple, so it's good. This 4 has red but no purple, so I have to jump that. And then on this side, there's both red and purple. So that says my domain starts at and includes. So I'm going to use a square bracket because negative 3 is included. I'm going to start at negative 3. I have to jump over 4. So I put 4 with a round bracket, union. I'm starting at 4 without including it and going to infinity. And there would be my domain. Okay? And if you look at the picture, you'll notice that this thing does not go past -3. It stops. It doesn't go anywhere past there. If you look at the table, you'll just get a bunch of error messages back there. Alright, so we look at this one. We have only radical drama. So I say, Mr. Radical, you must always stay positive. So if I solve it, square both sides, I get x plus 3 greater than or equal to 0. So x has to be greater than or equal to -3, which on a number line says I can include -3 and everything to the right. So my domain starts at -3 and goes to infinity, and never put square brackets on infinity. Okay? And notice that, see how this thing at -3, there's no graph over here. That's all going to be error messages. So my domain starts here, and then I can graph forever and ever that way. Alright, we've got two sets of drama again. We've got denominator drama, and we have radical drama. So my denominator drama says, Mr. Denominator, you may never equal 0, so x may never equal 5. On a number line, 5 is going to have a hole, but I can be everywhere else. Okay, so now I got to do my radical drama, which says, Mr. Radical, you must always stay positive. So square, square, and x must stay greater than or equal to 0. So that says I can include 0 and go to the right. So where we have both colors, not here, that's just green. We have red and green, red and green, red and green. Nope, gotta jump. Red and green, red and green, red and green. So if I describe the blue, I'm going to start at and include 0. And I'm going to go as far as 5, stop, jump it, start again at 5, and go to infinity. Okay? And then if you look at the graph, at 5 you can see there's a jump. And it doesn't go past 0. There's no graph back here. Alright. So it says, find the domain of each of these functions. A of s equals the square root of 3 over 4 s squared, where A of s is the area of the equilateral triangle with sides length s. Well, the domain, they're trying to freak you out because you see a radical and you see a fraction, but there's no letter under the radical, so that's no drama. And I have a denominator, but there's no letter in it, so there's no drama. There's no letter in the denominator, so there's no drama. No drama means that my domain is -infinity to infinity, all real numbers. Okay, this bottom one, if you look at the graph, you can see that there's a gap at -5 and there's a gap at 2. Okay, and that's because we say for my denominator drama, I say, Mr. Denominator, you may never equal 0. To solve that, just like if it said it equals 0, we say, well, that means x plus 5 can't be 0 and x minus 2 can't be 0, which says x cannot be -5 and x cannot be 2. So on a graph, on a number line I should say, -5 is going to have a hole and +2 is going to have a hole, but I can go, all the other x's are more than welcome to come. So there's my denominator drama. Now I have my radical drama, which says, Mr. Radical, you must always stay positive. So solve square, square. I get x plus 8 greater than or equal to 0, so x has to be greater than or equal to -8. So that would be down here, start and go to the right. Alright, so where there's red and blue, which isn't down here, red and blue, jump, red and blue, red and blue, red and blue, jump, red and blue, red and blue, red and blue. So this domain is going to start at -8, go to -5, union, start at -5, go to 2, stop, jump, start 2, go to infinity. Okay? Alright, so you try this one, hit pause, come back when you're ready. And hopefully you got negative infinity to 16. I have radical drama. So I say, Mr. Radical, you must always stay positive. Square, square, 16 minus x greater than or equal to 0. I'm just going to add x. Be careful though. Well, you know what? Let's not. You could, but I want to show you something. Negative 16 to both sides. I get negative x greater than or equal to negative 16. When you divide an inequality by a negative, remember that inequality flips. So this says that x has to be less than or equal to 16. And that's my only drama. So my domain is where there's purple, which is up until this point, which starts at negative infinity and goes to 16, and that's filled in because of the or equal to, so it's going to be a square bracket on the end. Yeah. Alright, try this one, hit pause, come back when you're ready. And hopefully you got 2. Alright, we've got denominator drama. So my denominator drama says, Mr. Denominator, you may never equal 0. So x plus 2 may never equal 0. X minus 5 may never equal 0. So x may never equal negative 2, and x may never equal 5. So on my number line, negative 2 is going to get jumped, 5 is going to get jumped, but everything else is welcome. Until we put our radical drama in. Okay, my radical drama says, Mr. Radical, you must always stay positive. So, square, square. I get x plus 3 greater than or equal to 0, so x has to be greater than or equal to negative 3. So I can start at negative 3 and include it and go to the right. My domain then is where there's green and red. Green and red, jump, green and red, green and red, green and red, jump, green and red, green and red, green and red. So if I describe the blue, that starts at negative 3, goes to negative 2, union, starts again at negative 2, goes to 5, union, 5 goes to infinity. Okay? Alright, so how do you determine the domain and range for a function? Well, domain, you say, Mr. Denominator, you may never equal 0, and Mr. Radical has to stay greater than or equal to 0. Okay? Alright, finding the range of a function. You're going to have to just look at the graph. Any horizontal breaks cannot be in the range. Okay, breaks in the range. Look for horizontal asymptotes. You can find horizontal asymptotes by these rules. If your top degree is smaller than your bottom degree, then your horizontal asymptote will be y equals 0, which means it will jump over y equals 0. It won't graph there. If your top degree is equal to your bottom degree, then your horizontal asymptote is going to be y equals whatever the top leading coefficient is divided by the bottom leading coefficient. And third, if the top degree is bigger than the bottom degree, there's not going to be any horizontal asymptote, but there will be a slant line. Alright, so if I look, it says find the range of each of these functions. If I look at the graph, so I type in 2 divided by parentheses x plus 3, I get this picture. Well, it looks like to me, this thing is doing this and getting close to 0, and this and getting close to 0. And watch, I can tell. My top degree is 0 because there's no x. My bottom degree is 1. When the top degree is smaller than the bottom degree, your horizontal asymptote is y equals 0. Promise, which means it won't graph there, which means I have to jump over that, which means my range is, it's going to go from negative infinity to 0, union, and then it's going to start again at 0 and go to positive infinity. Okay, my next one, if you look to see where there's going to be a horizontal asymptote, my top degree is 1, my bottom degree is 1. When they match, your horizontal asymptote is going to be the top leading coefficient, which would be 3, divided by my bottom leading coefficient, which would be 1, so I get an asymptote at y equals 3. Which means whatever this thing does, it's going to go from negative infinity, it's going to jump over 3, and then start again. And then let me show you on the graph. Sure enough, you've got this horizontal asymptote here at y equals 3. So my range goes from negative infinity to 3, union 3 to infinity. Okay, the next one, again, if I find my horizontal asymptote, the degrees match. My top degree is 2, my bottom degree is 2. When they're equal, your horizontal asymptote is TLC, 2, divided by BLC, 1, y equals 2. So I'm assuming my range is going to be negative infinity to 2, union 2 to infinity, but let's look at the picture. Oh. No, looky there. Okay, it doesn't actually go below, well, we have up till 2, right? But this thing doesn't actually go below 0, so my range is actually going to be from 0 to 2. Alright, on this one, my top degree is smaller than my bottom degree, so it's going to be y equals 0. Let's check the picture. Yeah, it looks like, see how this asymptote approaches it, and this asymptote approaches it. I mean, this part of the graph approaches it, and it crosses in the middle. You can't cross a vertical asymptote, but you can a horizontal. So again, my range would be negative infinity to 0, union 0 to infinity. And on this one, my top degree is bigger than my bottom degree, which means there's no horizontal asymptote, because there's actually going to be this slant asymptote in there. All right, so basically what that means, though, is I have graph everywhere from bottom to top. So my range here would be negative infinity to infinity. Alright, so you find the range of this one, hit pause, come back when you're ready, and hopefully you got that. If I look at my picture, alright, it looks like this thing doesn't even start until y equals 3. Then we start graphing. So my domain is going to start at 3 and go up to infinity. Alright, so range, you have to look at horizontal asymptotes and the graph. Domain and range, domain you can do algebraically. Alright, so we are at homework. Happy homework, and I will see you next time.